Okay, in this problem, I might think it's easier to actually multiply the x to 1/5 through. So x to 1/5 times x to the first, you get x to a power times x to a power, you add the exponents. 1/5 plus 1 gives us 6/5. So we got x to the 6/5, and x to 1/5 times 6 gives us 6x to the 1/5. Now you could use a product rule, but again, I think this would probably be easier. Now the derivative of that, x to a power, take your power, put it up in front, lower your power by 1. So 6/5 minus 1 would give us, actually let me write out the step, plus 6, x to 1/5, take your power, put it out in front, lower it by 1. So this is going to give us 6/5 x, 6/5 minus 1 gives us 1/5, plus 6/5. That's interesting that both are 6/5. And then 1/5 minus 1 gives us negative 4/5. Now to find our critical values, it's best to have this as a single fraction. Now I can factor the 6/5 out in front, not worry about it at all. This would be x to 1/5, and put it in fraction form, be over 1. Now this x to negative 4/5 I'll take down to the denominator in this manner. Anytime you move anything opposite of where it's at in a fraction, the sign of the exponent changes. Now our common denominator would be x to the 4/5. So now this one already has x to the 4/5, so I don't have to do anything with it. This would be 1. Here I multiplied the bottom part by x to the 4/5, so I have to multiply the top part by it. Oops. Let's try it again. Okay. Then we got 6/5 times x to 1/5 times x to 4/5, x to a power times x to a power, you add the exponents. 1/5 plus 4/5 is 5/5, or 1. So that's x to the first over x to the 4/5 plus 1 over x to the 4/5. So we got x plus 1 up on top, and we got x to the 4/5 down below. Now I'm going to come back to this version right here where I'm finding the second derivative. But now, to find our critical values, you can set the top equal to 0, and you can set the bottom equal to 0. And we get x is equal to negative 1, and x is equal to 0. If I build my table here, I want to plug those in to my first derivative here. Now the 6/5 is positive, so I don't need to worry about it. But I'm going to plug it into here. So choose test cases. I'll choose something less than negative 1, like negative 2. Something between negative 1 and 0, like negative 1/2. And something greater than 0, like 1. Now if I plug those in here, I'm going to have negative 2 plus 1. And when you got x to the 4/5 power, this 4 up on top means this is always positive, so I don't need to worry about that. Negative 2 plus 1 is negative 1. Negative divided by a positive is negative, which means this is decreasing. Now if I put a negative 1/2, I'll have negative 1/2 plus 1. And again, anything to the 4/5 power is always positive, so I don't need to worry about that. Negative 1/2 plus 1 is 1/2, which is positive. Positive divided by positive is positive, so this is increasing. If I plug 1 in there, 1 plus 1 over, and again that's positive, so 1 plus 1 is 2. So this is going to be positive, so this will be increasing. So it's decreasing from negative infinity to negative 1. It's increasing from negative 1 to 0, and increasing from 0 to positive infinity. Now here, See where it's decreasing from negative infinity to negative 1. But then the interval of increase went from negative 1 to positive infinity. Since we got negative 1 to 0 and 0 to positive infinity, these can be merged together, such that it's negative 1 to positive infinity. That's not always the case. If it's not defined at x equals 0, then you can't do that. But our domain is such that it is defined at x equals 0, so that's fine. Okay, now here, this is decreasing, changes to increasing, so this is going to be a min. Now this doesn't change, so there's nothing here. So we're going to have a min, and we'll put in negative 1. This is the value that we're using, negative 1. And we plug that back into our original function. Well, if I plug in negative 1 here, negative 1 to the 1/5 power, that's like the 5th root of negative 1, which is negative 1. Negative 1 plus 6 is 5, so that gives me negative 5, assuming I'm doing my math correctly. And I guess they're just wanting the y part, they're not wanting the point. But you see this a to the negative 5. Now there is no max, that's why it does not exist. Now to find our inflection points, the concavity, so forth, we would need to find second derivative. And this is what we want to work with here. We got 6/5 out in front. X to first over x to 4/5. You subtract, this is 5 over 5, so that would give me x to 1/5. Plus x to the negative 4/5. Now that's our first derivative. So to find our second derivative, take your power, put it up in front, lower your power by 1, minus 4/5, take your power, put it up in front, lower by 1. Okay, so then this becomes 6/5 stays out in front. Then I got 1/5 x to the negative 4/5, 1/5 minus 1, minus 4/5 x, negative 4/5 minus 1 is negative 9/5. Now I can factor 1/5 out, makes it a little bit easier. And I got x to negative 4/5, which is 1 over x to the positive 4/5. And this 1/5 is gone, so that leaves me a negative 4. So minus 4 over x to the 9/5. Okay, so that gives us 6 over 25. We want to get a common denominator. And when you got x to a power and x to a power, you always go with a larger exponent, which is 9/5. So we're going to rewrite each one with that new denominator. Now this one already has the next 9/5, so we're fine here. Here we multiply the bottom part by x to the 5/5. We have to multiply the top part by x to the 5/5. So we're going to have 6 over 25, and that's x minus 4 over x to the 9/5. Okay. Now for our critical values. You set top equal to 0, x minus 4 equal to 0, and set the bottom equal to 0. And we get x is equal to 4 and x is equal to 0. Okay, so if I build my table of intervals, and I want to choose test cases, something less than 0 like negative 1, something between 0 and 4 like 1, something greater than 4 like 5. And we want to plug these into our second derivative, which is right here. First off, the 6 over 25 is positive. We don't need to worry about it. But if I plug negative 1 in, I got negative 1 minus 4 over negative 1 to the 9/5 power. Negative 1, negative 4 is negative 5, and if I put negative 1 to 9/5 in my calculator, I'd get a negative value. So negative divided by negative is positive, which means this is concave up. Now if I plug in 1, I got 1 minus 4 over 1 to the 9/5 power. 1 minus 4 is negative, and 1 to the 9/5 is positive. Negative divided by positive is negative, so this is concave down. Now if I plug in 5, 5 minus 4 over 5 to the 9/5 power, this is positive. 5 minus 4 is positive, 5 to the 9/5 power is positive. So positive, this means this is concave up. Now, since our concavity changes here, this is our inflection point, and this is our inflection point. So we'll have 0 comma something, and we'll have 4 comma something. Let's see what they're wanting. They want to point here. That's interesting. Up here they don't want to point, but here they do. To get these values, what you do is you plug these back into your original problem, and that will give you this. I won't go through that. These are our intervals, where it's concave up, concave down, so that's just going through writing this down. But that should be how do you work that problem?